Okay, so we're going to continue where we left off the last time, and that's going to be in section 9.6, which is looking at the graphical disc cam profile design. So this is where now we're going to use that information from the displacement diagram. So we looked at creating the profile on a displacement diagram in the beginning of this chapter and looking at how the follower has to move. Now what we're going to do is we're going to actually create the profile of the cam from that. Okay, so as we look at page 237, figure 918, we're going to look at kind of each of these important vocabulary words, if you would. And we're going to go look under here. So we're going to specifically look at figure 918 here. And this is going to give us the kind of the basics of cam profile. So up until this point, we've been looking at just the follower and what the follower has to do, because the follower ends up being what we would call the output, like the output motion that we're trying to achieve. So when we talked about, the follower has to rise and fall and such, and we created a displacement diagram using harmonic motion or cycloidal or constant velocity, that was all about the follower. Now, to get the follower to do that, we have to create the profile that it is going to follow, which is called the cam. Okay. Now, as we had stated last time, this follower has to remain in constant contact with the surface of the cam. And as this rotates around, okay, you'll notice that it's not a constant diameter. Okay. If it was a constant diameter, it would remain in the very same place. It wouldn't move, in and out at all. But because there is a difference here, and as we rotate, this is actually going to go up and down as it is in contact and as this rotates in either a clockwise or counterclockwise direction. Okay. Now, a couple of things here. Number one, the base circle. The base circle, as it's pointed out here, this is the circle that's created that if we would not have any follower movement at all, it would just remain in that same place. That's called the base circle. Okay. That's going to be the circle at what we would identify as our home position or our 0 degrees on our displacement diagram. Okay. Then you're going to notice that we have a prime circle. Okay. The prime circle is the circle that the center of, in this case, the roller follower is going to actually follow if, again, it would be on the base circle. All right. The next circle that we have is going to be the cam profile itself. And then lastly, we have the pitch circle or the pitch curve or the pitch. It wouldn't be a circle because it isn't a full circle, it's a curve. And that's going to be the center that our follower follows as it's in contact with the cam profile. Okay. Now, this is a nice illustration to kind of show you how it relates to the displacement diagram. So if we look here, this base circle, if we just kind of think about cutting it and then rolling it out, if we look at a displacement diagram, the one up here, that base circle is represented by this line right there. Okay, it's kind of like our 0, our start point where everything is starting to happen. And then as we go back over here and we start taking movements, do you see how from the base circle here, if I look at this distance, now it's not going to be constructed exactly this way. It's going to represent, for instance, I'm going to go that number of degrees. That's going to be that distance from the base circle up to now the movement that I need. Okay. When I get to my highest point here, that is going to be reflected in, for instance, the largest distance between that base circle and the cam profile. Okay. And then we continue to go around, if you would, and you're going to notice that here's that largest distance. And then as we kind of come back around, that distance keeps getting smaller and smaller until it then goes back to that 0 point, which is back on the base circle. Okay. So this is what we're doing. We're kind of putting in circular path, what would be on our displacement diagram in like a flat or a linear motion. Okay. Just going to catch ourselves up using the distances from the displacement diagram. So there's a number of different types of follower configurations that we can use for for our follower as we construct our different cams. And we're going to start looking at those on the following page and see how they relate back to the corresponding displacement diagram. So on page 238, you're going to notice that we have a displacement diagram here on the top. Now, the easiest type of cam to create is going to be the inline, and in this case, the knife edge follower. Okay, you're going to notice that we don't have as many circles around here because we only have to worry about the contact point. All right, and how it's in relationship to the circle. Additionally, because this is inline, the distances are going to directly reflect based on the angles that are here. There isn't as much construction to do as we have to do in some other ones that are coming up. Okay, so basically what we have to decide is, okay, our 0 position on our follower. Now, this could be the follower at an angle. This could be an offset, but in this case, they have the follower directly vertical above the center of rotation. It can be anywhere around this circle, but this happens to be where they're starting. Okay, so as we look here, this is going to be vertical movement only of that follower going, up and down. Okay, now the point, the knife edge point here that it has contact with, and we just have to draw it exactly as that. All right, if it's a roller, then we have to draw a roller. We'll see that in our next example. Okay, but this one is a knife edge, so again, it keeps things simple. Then what you're going to notice that you're going to do is they have in 30-degree increments the mark-offs of each one of the kind of the main points along our cam. So they have this in 30-degree increments. Okay, and then what we're going to do is we're going to notice that if our cam rotates in a clockwise direction, that means that our angles are going to have to go in the opposite direction. So if this is our 0 and we start here and we start going in this direction, that means that the 30 degrees is going to be the first 30 degrees coming from there. So we actually number counterclockwise if the rotation is clockwise. Okay. All right. And then all we do is we have to draw our base circle as our 0. And then we have our construction line for each one of the angles here. All right. And then where it comes in contact with the base circle, you'll notice they have a delta R, which is a distance, and then 30 is going to correspond to the number of degrees that were along our displacement diagram. So if we go up here, if this is 90, this would be 60. Here's our 30 degrees. We would measure that distance. Okay. So in CAD, we can, just get a little distance off of there. If you're doing it manually, then you have to, try to be as accurate as possible. But this is going to be the distance then that we translate to along that line. That would be a point that we would create. Okay. Then we're going to do the same thing at 60 degrees. All right. So we go to the 60-degree mark and you're going to notice, all right, now I'm going to mark off this much. Now I know this mustn't be to scale because it's definitely not that long there, but from that point where the 60 degrees comes through the base circle, and then we would mark off that distance that it would be underneath the displacement diagram at 60 degrees. Yes.
Now, is that past the baseline circle?
Correct. Yep. Mm-hmm. Yep. If you look here, here's the base. And then this is the distance right in between here. That's going to be that delta value. Then we go to 90. And you're going to notice again, this is a lot taller than what they have there. So it's obviously not to scale, but that distance then would go from the base circle and then out along that 90-degree line, you would mark now your next point. And you continue to do that every 30 degrees for the total of 360 degrees. So there's quite a few points that you would go along and you would create. Okay. And then once you have all of those points around the outside, then you just simply go into AutoCAD and you do a spline fit through those points and it creates the profile. Okay. So this one's very straightforward. Any questions kind of on that process? All right. The next one we have, yes.
Is it 30 degrees standard, or is it based on the problem?
It really depends on, for instance, the problem, and then also how accurate you need it to be. The more points you have, the more accurate that that spline will be, because you'll have more points along it. So you get to be the judge as the designer. I believe for the problems that I have you do, I'd have you do them every 30 degrees. And that's, I mean, anything less, it's going to be pretty crude. Anything more, it starts to get to be, you know, a lot to do. So I think it's a happy medium. Yeah. The next one you're going to notice is very similar, except this time, instead of a knife edge, we just have a roller. So there's one extra circle, or I should say, I guess, two extra circles, or one extra circle and one path. So an extra circle that we have is going to be the trace circle, okay? And then the other one is going to be what they call the pitch path. And that's going to be around here where those rollers are going to sit. Now, the only difference here is the construction of the base circle is the same. And if you're going in a clockwise direction with your rotation, then you're going to go counterclockwise with your angles. Since it's in line, all of these lines come directly from the center, okay? And then what you're going to do is you're going to strike then a circle that is going to be the trace circle, or I'm sorry, the prime circle, not the trace circle, the prime circle all the way around, which is going to be the center line of your roller, okay? Then at the center line of where that crosses, you are then going to, from your prime circle, you're going to find your distance at 30 degrees that's offset from your base. So here, you're going to notice that this would be my 30 degrees, my delta R, and that would be from the center of that prime circle. And then along that 30-degree line, that's going to be the distance that we have, you know, marked off. Okay. And then you're going to put that point there. That's going to be the new center then for the roller position. Then you're going to do that same thing. You're going to go to 60 degrees. You're going to find where your prime circle center is from your roller. And then this distance right here is going to correspond to the distance that you would measure off of your displacement diagram. Okay. And then that's going to be that center. Now on each one of those new points that you have, you're now going to see, you can see that you're going to put the roller, okay? And then through the end point of the roller is where you are going to then do your spline, okay? So those are going to be tangent points along there, right? So just another way to construct. But this time, because we have a roller, we have to go tangent to the roller as opposed to the knife edge points. Okay.
What are you basing your prime circle off of?
The prime circle is the center of the roller. And that is going to be if our base circle, and that'll always be given to you. The base circle will be given to you of the roller. The roller, exactly. Yep. So if you pull this around, this makes the perfect circle as if it wouldn't even move. So it's this distance from here,
okay,
all the way around.
that's only if the cam then is like circle like, or you like
Well, this is because there's a roller on your follower.
okay.
Yep. So the difference is over here, we have the knife edge and it has direct contact here. So this is the most simplistic one. So now over here, because we have the roller, we need to find the center of the roller each time. And then your spline is going to be tangent points along the inside as opposed to actual points that intersect.
All right.
Okay. So the construction is slightly different, but it's very similar. Okay. Still in line here. And that's why our angles are then going to come to the center of the rotation. All right, let's look at an offset roller. Okay, here's an offset roller. So there is a little bit different construction here. And how this works is your base circle again will be given to you. All right, and the position of how offset your follower is going to be. Now, because this is a roller follower, we have to draw the roller on the end. And you're going to notice that now what's going to occur is from the actual center of rotation to the center of our follower, there is a radius right here. And that's the distance between the two. Okay. Now there's going to be a new circle that goes around here. All right. Now our 0 degrees is going to be the first one that's going to be perpendicular or 90 degrees to the side of that. And then what's going to happen is we're going to divide this inside smaller circle in 30-degree increments all the way around. So where this then is going to be intersecting that, I guess they call it the offset circle, you're going to be then 90 degrees in this direction, and that's where my 30 degrees is going to come up. Okay. And then you're going to have that same prime circle going all the way around. And then you're going to then off of that prime circle along your angle, you are going to have then the distance corresponding to the angle on the displacement diagram. And then as you get your roller in the new positions all the way around, your cam profile will be tangent, 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 tangent to each one of those on a spline. Okay. So this is an offset roller. Let me look for just a second because I wanna remember the homework problems that you guys are doing for me. The first one is going to be reciprocating. It's an inline roller follower. Okay, so number 39 is an inline roller follower. So it is going to be like this one. Okay, it's going to be like this one. The second one that you're going to do for me is going to be an offset roller. So that's like this one that we're looking at here. Okay, an offset roller right here. So this one you're going to want to kind of pay close attention to. Right. The next one, as we go on this offset, it's going to be another 30 degrees, and this is going to correspond then to 60. So here again is a 90-degree angle, and then your angle is going to go off at 60 degrees here, perpendicular back, and then your distance is going to be from your prime circle, and this is going to be the distance from your displacement diagram. And then you continue to go around and then perpendicular, around, perpendicular, around, and perpendicular. So this right here is not 30 degrees, okay? Remember, this is your 30 degrees here, and then your perpendicular back up. Same thing with the 60. This is not 60 degrees from here to here. It's 60 degrees here, but then perpendicular to it is going to correspond to the 60-degree position. Yes. Yes. Yeah, so the prime circle is going to be, if you are, here's your base circle right here, and your prime circle is going to be where it would be in relationship to the follower, as if it would be on that same position all the way around. So you'll notice that it's if we look, trying to see where the center is here. Here's my center. And you'll see that this circle is offset just slightly because its center is going to be down here, and it's going to be offset half of that distance that the offset occurs. These two require laying it out in CAD, right? So you'll have all the information, and once you start kind of constructing these, it'll start to come together. So this offset circle is based on the radius of that offset right there. So that's where you're going to start. And then you're going to put each one of these out, okay, perpendicular to its corresponding line. So there's a little bit more construction because of the offset. Additionally, in the book here, it does give you the procedure starting on page 239 for the offset roller. So if you wanted to, you can also follow that as well if you have any questions, or me, okay? But it does give you step-by-step how to kind of go through that using this illustration, okay? And then again, once you get your positions of your roller, you have to show the roller in the position. So the cam is not at the points that you could create. The center of the roller is at the points that you create. And then the cam profile is going to be tangent, 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 tangent as a spline all the way around. Okay. All right, so those are the two that you're going to be interested in. The next type that's here, you won't have to do this for homework unless you really want to. You could find a problem in the back. But this one is a flat-faced follower. And in this case, you have your angles again, and then each time you're going to be perpendicular to that corresponding angle, and then your offset is going to be again on the angle that corresponds to the displacement diagram distance. Okay, so there's that one. We didn't do this one. This one's kind of fun, but this is the pivoting. So there's a little bit more construction, probably the most intense construction of all of them, but I didn't have you guys do that one. If you wanted to, again, you certainly could. But here you're going to notice that for this cam follower, this one actually pivots out of position. So then you're going to have a pivot circle around the outside at each one of the angles. And then you're going to show your cam follower on each one of those positions. So that's that. But again, you don't have to do this one for your homework. The two that you're going to focus on are going to be the inline roller and the offset roller. Okay. So if we take a peek, get back over here, saw the procedure for that one, offset roller procedure. And then the last thing I want to talk about is pressure angle. Okay. Pressure angle is going to correlates the follower to the cam pushing force and the side load generated within the follower that are not in line with the center of rotation. So what ends up happening is if your pressure angle gets too large, you could kind of jam that follower if possible, if it occurs. So you want to keep your pressure angle right around no more than 30 degrees. If you start going over 30 degrees, then you risk having a jam. So if we look at figure 925, here, you're going to notice that the pressure angle is going to be, when we're rotating and we look at our contact force, it'll be perpendicular to the actual surface of our cam. Okay. Now, when we have an offset roller or offset follower, like we see here, and our force is not going through the center, we have a pressure angle that occurs. And that's the angle that they're saying not to exceed 30 degrees. Now, if you do for slower moving applications, it's usually not a problem, but it's when it's faster moving applications that it can be a problem. And then there are some ways that you can correct that by changing the size of the base circle and, minimizing the offset and things like that, if possible. Okay. So just be aware that pressure angle is something that when we're dealing with cams, that we want to make sure that we kind of pay attention to that. Okay. So if you need to decrease the pressure angle, you want to increase the size of that base circle, decrease the magnitude of the follower displacement, or increase the angle that cam rotation is on the rise and the fall. So not making it as steep and as steep in each one of those directions, kind of distributing it over the cam profile. So that takes us to the very end. So this is the last part of CAM design. So you'd be ready to work on now all the homework that we have assigned. So if we go to assignment number 6, you have 4 problems to do here. And we already introduced the first 2. The first 2 are going to be displacement diagrams, and the last 2 are going to be our CAM profiles. So let's take a peek at the end of the chapter here and just review the problems that you have assigned. So the first one that you have is 9.7. This is on page 254. We have a cam drive is used as a mechanism that tests the durability of an oven door. The cam follower must rise 2 inches with harmonic motion in 1 second, and then dwell for half a second, and then fall 2 inches with harmonic motion in another 1 second, and then dwell for another 1. And then it's going to repeat that sequence. So determine the required speed of the cam, that's the W, and graphically plot that displacement diagram. Okay. So what you have to be aware of is the harmonic motion here means that you have to construct that curve. Okay. So to construct the curve, you want to go back towards the beginning of the chapter. And actually, on page 232, this is an example of how you would construct the harmonic motion, either the rise or it would be a mirror image on the fall. Okay. Now, as you kind of determine like how long your displacement diagram is going to be, a good place to start, I'm not saying it has to be this, but for instance, if your total rise is 2 inches, then the length that you want to make your full 360 degrees is about 3 times that. Okay, that's a good place to start. Now, if you find that it looks a little steep or it's a little long, you know, you can adjust that a little bit, but I would try to keep it to kind of nice numbers to work with. So maybe to the inch, because then you have to try to figure out distance wise, how many degrees are along an inch, or how much of an inch is actually a degree. So if you work with, you know, funny numbers, meaning that they're not a nice increment, then it's harder to figure that out. Okay. So if you have any questions as you're constructing, you know, let me know, but use this as your guide. And then it also has a nice step-by-step procedure if you would follow that. So that's the first one. The second one that you have is going to be number 9. And here you're going to be using cycloidal motion for the rise and the fall. And the construction for the cycloidal motion is on, well, that's an example of it. I thought, okay, here we go. Is on page 233. Now this happens to be on the rise, but the fall would be the mirror image. And you'll notice that it has this line going straight down, and you can pull this away, you know, as far as you want to. To get the radius, you're going to need to know what the height is, which is going to correlate to the rise or the fall dimension that you have. And then you're going to mark off 6 even increments, not in even angles. It's just however long this ends up being along your axis, you divide that then into 6 equal increments. And then you're going to divide your cycloidal circle into 6 even increments. And then you'll notice how you pull together the 2 and the 1 to the center, and then that's going to plot on the points that correspond. And then the 4 and the 5 are going to be here. And then the 3, 0, and the 6 are all going to fall in the middle. So 0, 3, and 6 are going to be along that line. And then it's going to be a spline fit in AutoCAD. Okay. So that problem, you're going to be using that construction. Then the last 2 that you have are going to pertain to what we talked about today. And this is going to be creating the profile of a plate cam. And you're going to be using a reciprocating inline roller follower. Okay. And the roller diameter is 1 inch. The cam must have a base circle of 3 inches and rotate in a clockwise direction. So in the direction that we saw in our example or on the diagrams, and then graphically construct the profile and then estimate the largest pressure angle. Okay. Now this is an inline. Okay. So think about that. Now, when we look on the next one on 41, this one is going to be a very similar. Oh, before we go on, the displacement diagram is directly above here on page 256, and they give you the cam angle and the corresponding follower displacement. So these are the numbers that you're going to look to. Now, you don't have to do it for every 10 degrees. You're going to do it for every 30 degrees starting at 0. Okay, 30-degree increments. So you're going to pick out 30, 60, 90, 120. So not all of these, not all of the values. Just every 30 degrees. And then here we have a reciprocating offset roller follower, and the offset distance is 3/4 of an inch to the left of the cam center. And then the roller diameter is 1 inch. Cam must have a base circle of 3 inches and rotate clockwise again. So graphically construct the profile and estimate the largest pressure angle. Okay, now this is an offset one. So estimate that pressure angle. So as we look back again, where you're going to be looking for construction is going to be on page 240 for the offset roller here, using the information you got. And then for the inline roller on page 239. And then on the pages previous to that, they have the corresponding procedures. So the rest of the time you have to work on this, and I'm available to help you with any questions that you may have. But before I kind of stop the recording here, does anybody have any questions?
What would be the best way to drawing, when you draw the diameter of the radius of every other circle? Real basic, you don't say after line, a good circle for drawing that cam graphically, would it be best to just create
all the circles first. Yep.
and then just drag an arc on the tangent points or the intersection?
Not an arc, you want to do a spline.
Okay.
So if you're in AutoCAD, and I don't have my AutoCAD, oh, well, maybe I'll open it up here. That's a good question. So you want to use a spline, you don't want to use an arc because you'll exhaust. I think arcs are only like 2 or 3 points. So if I go in here, let me just open my AutoCAD first. I'll show you where the spline is. And this is what you would use for the displacement diagram as well. When you find those points along the X and Y axes. So I'm going to close that. And so when we are in, I just want to start, I want to do a new, and I'll just take that one. That's fine. Get rid of that. There we go. So what you'll do is you'll create your points. All right. And then underneath the draw menu right here, here is the spline fit. Okay. And now you can either pick points or tangencies. So in the case of the roller, you're going to go tangent, 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 tangent. And then don't press escape, press enter at the end. Otherwise you lose the whole thing. Sometimes we can end a command with escape and it's no problem, but on the spline command, you have to press enter. Otherwise you're going to start all over again. So yeah, those would be the tangencies then, and then the spline will create that going through. Yeah.
All right, thank you.
You're welcome. Any other questions? Oops. Mm-hmm.
Page 937.
So for this, let's see, let me go underneath. So for both problems, oh, I think I disconnected here, sorry. For both problems, the displacement diagram is on page 256. So the diagram is here. And then it has the, all the information of the corresponding angle to the follower displacement, but you guys only have to do every 30 degrees, not every 10 degrees. All right. And that's for both numbers 39 and 41. Same displacement diagram. Yeah. All right. All right. If there aren't any more questions, I'm going to then stop the recording here, and then I'm available with whatever you need.